Hi everyone, welcome back to our channel. Today we are going to discuss the power electronics control of electric motor drives. Okay, so what is the need of this power electronics control of an electric motor? Especially, I'm going to focus on the three-phase induction motor. So let's try to discuss one by one. Then we'll go into the picture. So actually, uh, we want to in an electric vehicle we are having a battery which is nothing but a DC supply. We need to convert this DC supply into an AC supply. Why? Because our electric motor, especially to what I'm talking, is an induction motor. We need to convert this DC supply into AC supply. This is possible only with the help of a inverter. So with the help of inverter, we need to convert this DC supply into AC supply, where this motor is called induction motor. Now let's try to see here how this inverter action is taking place. And here, to have this better control, I'm selecting sinusoidal pulse width modulation technique. So how this technique is employed and how it is going to control the speed of an induction motor, I'm going to discuss right now. Let's try to see the circuit diagram. So I'm taking the circuit diagram. I'm having a DC supply, and this DC supply is divided into two parts, and this is applied to a transistor, or you can take IGBT switch, whatever is comfortable of switching. Generally IGBTs are selected, and in parallel to this we are going to have one diode, and here we are going to have one more diode, and it's connected like this. Okay, so this I am going to label as a switch S1, this diode. The purpose of this diode is to provide a path for reverse current. So this diode provide the path for reverse flow of current. It provides the path for reverse current to flow. Now, so this is one leg. We have three legs. We are going to select the another leg. So here also you are going to have the switches, and the connection is established like this. This is another switch. This is another switch. This is having an parallel diode, and I'm giving the label as D3, and here I'm giving a one more diode in parallel. I'm going to give the labeling for this diode as D6, and here we are going to connect it. So just to differentiate only, I'm giving using different colors. So here they are interconnected like this, and this switch, the labeling I'm giving it as I3, sorry, S3 as well as S6. Okay, and we have R, Y, B. Let's try to take B here. Okay, so here also you are going to have a one more switch, and to this switch we are going to have an anti-parallel diode. I'm labeling this as D5, and here I'm going to label this as a some D2, and we are having an connection between these two, and we are going to join the both ends. Now this switch I'm going to label as similarly as S5 as well as S2. Very simple. Switch 1, switch 2, sequence 1, 2, 3, 4. Okay. This is D4, this is S4. 1, 2, 3, 4 is nothing but diagonal. 1, 2, 3, 4, 5, 6. Okay. Or you take this as leg 1, leg 2, leg 3. Generally this way only we'll try to charge it, and we are going to connect this to an transformer. And from here, so rather than explanation, this diagram only is consuming more time, no worry, but we'll have a clarity of how to do it. So I'm taking the winding as star, so red is over, and we'll try to go for the black color. So here we have one more tapping, and we're taking the tapping, and from this tapping we're going to connect it to the another phase. It's nothing but take this as R dash or RR, take this as Y dash or YY. And next we are going to have the one more wire. Okay, just a small modification. You connect this directly here, and directly you will take it out. Okay, so I'm taking this winding outside like this, and I'm going to connect the sequence of YY, YY, and only Y, R, Y, B. So this is nothing but B. This is R, Y, B. So now you see here, it's very simple to understand. There's nothing else to get confused also. So for three phases, we are drawing three winding. Now can you say what kind of connection this is? This is like a star connected system. Okay, so how to identify the star connected system? Let's try to have a look. So actually, if you take any winding, you're going to have R. This is one set of winding in the three-phase induction motor. This is one more set of winding. This is and one more set of winding. So this is R. This is RR. One set of winding. This is Y. This is another set of winding. I mean another terminal YY, and this is nothing but R, Y, B. Three phases. If when you join the all RR, YY, BB, then this is going to construct a star network. The secondary terminals, I mean the extreme ends of RR, YY, or you can join, if you change it also, if you join Y, R, Y, B to one point, this point will act like a neutral point, therefore this connection is called star network. But how to construct? So here you can understand our induction motor is connected in which fashion? Star connection. So now let's try to come to the delta connection. So in delta also we are going to have three windings, and we are going to label these windings as R, RR. Next one we're going to have Y. Okay, so this is next set of winding Y, YY, RY, B. So this is another set of winding. So RY, B, BB. Or you can write down R dash, Y dash, B dash. Nothing else. Just I want to identify the terminals of the motor. So now these two terminals I'm going to join or short circuit. So I'm going to short circuit these two terminals. I'm going to short circuit these two terminals. Then what it is going to construct? This is similar to that of an delta. So this is how to connect of a winding, I mean the stator of a three-phase induction motor in the form of an delta. So here generally for induction motor we will control the pulses or whatever you do will give the supply to the stator, and rotor is connected by a concept called induction. So depending upon the squirrel cage or slip ring it will try to operate. So we will generally excite only the stator. Why? Because it works on the principle of induction. So this is all about how we connect the induction motor. So now we have been successfully converted, we are planning to have. So here we require the voltage which is nothing but so this is nothing but R, Y, B, where this R, Y, B are nothing but AC supply, but what is the input we are supplying is DC. How to convert this DC to AC? With the help of this 6 switches or with this network, where this network is called as inverter connections. Now let's try to go what actually internally happen or how we are going to do it. So in order to do it, we are going to generate the pulses. In order to generate the pulses, I am taking a reference signal where the signal is called as a sinusoidal wave generation. So I am having an sinusoidal wave generation, and this is fed, and this is one, and this is another, and this is another summer. So here we are going to compare with one more reference, where here we are going to call this as a carrier signal. Okay, so this signal what we are going to generate is called as a carrier signal, and the signal I'm going to generate, which is nothing but an one. So you can see here 3. So I'm generating a triangular waveform. So this is an triangular waveform which has 6 triangles in an cycle. So I'm taking the 6 triangular, I mean 6 triangles are there in one cycle. In such a way I'm selecting. So like this, I'm taking this as R phase, I'm taking this as a Y phase, I'm taking this as B phase. So similarly, we'll have an interconnection from this carrier signal generator, which is nothing but a triangular wave, and this is nothing but comparator. They are going to compare each signal, and the resultant signal is given to a block, where this block is called a saturation block, and then we are going to exit the switch S1 as well as S4. From here, after comparing, we are going to have an saturation, and we are going to exit the switch S3 as well as S6, and then we are going to have an saturation, and we are going to run this switch, which is nothing but S5 and S2. So now we can see here our sinusoidal waveform, where the sinusoidal waveform we are going to call it as reference waveform, where this triangular waveform we are going to call it as carrier signal. We are going to compare the signal, and resultant is filtered between the minimum limit as well as to the outer limit, and it is subjected to the switches with the help of a gate pulse. So here to this gate pulse we are going to subject S1 S4 like, and then second, whenever S1 S4 is on, similarly this complete S3 S6 S5 S4 is in off. When S3 S6 is on, remaining are in off. S5 S2 is on, remaining 4 are off. Like this, a sequential switching we are going to perform with the help of a gate pulse. So now this is what's happening to S1 S4 S3 S6, and let's try to draw the important diagram. So this you have to draw of your own, then only it goes into the brain. So now we have to do the comparison action. So how to do this comparison? Let's try to see with an diagram. Okay, so try to focus. So in order to draw more clearly, I'm taking only half cycle. Why? Because a complete cycle also you have the same, but if you draw more than half cycle, it is more than sufficient to understand how the pulses are generated. Let's try to draw it. So focusly listen how the waveforms are obtained. Actually this will be obtained from an CRO. So you are having an x-axis, which is nothing but omega t. Here I am going to have one sinusoidal waveform. Okay, so this is one complete sinusoidal waveform, and I am going to have negative. You can take it into negative or you can take it into positive. Okay, so in this cycle I want to generate, this is nothing but which waveform? The reference waveform, or the reference sinusoidal waveform we are generating. And now we are going to interface this, or we are going to compare with an triangular waveform, where it should have 6 triangular waveform at the given time. So here you should have here, but up to here how many you need to have? 3 triangular waveform. Only that only I am drawing in order to make you very clear. So the triangular waveform is like this. It goes up, and one is completed, and exactly at 90 it will come to the down, and it grows up. Okay, and then it, this is nothing but it has to come down at one more point, and it has to reach this point. Okay, so this point is nothing but exactly we'll be having at 180 degrees. Okay, so now you can see here almost all, this is triangle 1, triangle 2, and this is a triangle 3. So here how many triangles we have in experience? 1 2 3. So 3 triangles are there, and we need to compare the values. So the output what you're going to get here, which is nothing but so this is the output of an sinusoidal pulse width modulation signal generated after comparison. So when you are going to use a comparison, as I already told, we are going to compare. Here, when the waveform has to be generated, so we are going to write down the condition. Okay. So this black color, I mean this red color, I'm going to call it as an carrier signal, and this I'm going to call it as a reference signal. So the condition here is whenever VR, I mean the reference voltage is greater than VC, then only you can have the output of the comparator. You can see in this gap you can have it. So here VR, this is nothing but black color line is more greater, but VC is of lower magnitude, then automatically a pulse is generated. And next one, here if you see this, here what is greater? So here VR and VC relation, and you see this VR, so VR is greater, no. So we take this reference voltage, so we are going to have VR is lesser. Okay, so this is the VR is lesser, automatically here we don't have. And when you come here again, you compare the condition here, VR should be, and VR and VC, where is VR? So this is nothing but VR. Okay, so this is nothing but VC, and you can see here the reference, this is greater. Okay, this reference is greater and VC is lower, so this is nothing but VC is lower, VR is greater. Okay, so in this duration again a gate pulse is generated, and this pulse will have more width. And next condition, so here also the condition is violated, VR reference is greater than VC, but here VR and VC relation, if you see here, VR is nothing but lower than VC, VR is less than. Why? Because you can see the height, so VR is lesser, but what is VR is less. VR, I mean VC is less, but VR is greater. So like this, we are going to have VR is greater than VC. So here also you can see here VR. So VR is nothing but which one? The reference one. So reference one we are going to have higher, but VC is of lower magnitude. Automatically, one more gate pulses are generated here with this interaction. So you can have a lesser pulse width. So this is the output of an sinusoidal. The condition is very simple. The magnitude of reference should be greater than the magnitude of VC. So this reference is an sinusoidal magnitude should be greater, where the triangular magnitude is lower. You can see here sinusoidal is greater, VC is lesser. Sinusoidal is greater, control is, I mean uh, triangular wave is lesser. Here sinusoidal is greater, where the triangular waveform is of lower magnitude. That's why here we are going to have the output. So I can draw for remaining, but when you consider in positive or negative also, you'll get the same. So you'll get like this. Okay. So I don't want to elaborate it more, because I got the required output. So this is nothing but a sinusoidal pulse width signal generated from the comparator. Based on this, we are going to trigger the complete circuit, and the resultant waveform you are going to expect is the same waveform what you are directly getting from the here with the same intervals. You are going to the same output. So here you have been got the pulse width like this. Okay, so this for half cycle I am going to draw. So within this half cycle, how many pulses are generated? 3 number of pulses are generated. Okay, so this waveform, I mean the reference waveform, oscillates with the frequency of FR, where this control waveform or triangular or carrier waveform operate with the frequency of FC. Okay, so now later we'll derive it. So this is the output what you are going to get, and if you join the heads of this, you can see here this is an sine similar to an, it's not a sine, it's like we will call it as a modified sinusoidal waveform. So I can see here, here what we had performed is a sinusoidal pulse width modulation technique. So this technique of getting this waveform is called sinusoidal pulse width modulation technique. So modulation means controlled output. You can see here the sinusoidal waveform is obtained and the pulse width is controlled. You can see here, so you're having low pulse, width is lesser and width is of greater and width is of lesser. So we, by using this sinusoidal wave as well as a carrier wave, we are trying to vary the width of the waveform. That's why it is called sinusoidal pulse width. So pulse widths are adjusted, pulse width control or adjusted technique. Sir, what is the importance of this sort of waveform? So you can see here, the magnitudes are smaller and the magnitudes are higher continuously. So when you give this sort of input to a three-phase induction motor, automatically they are going to be operated to produce 100% rotating magnetic field, and they have an controlled output. Means, what is the meaning of controlled output? Means, so flux phi is equal to V by F. We are going to control the output voltage automatically. Flux is controlled. If automatically flux is controlled, automatically the speed of the induction motor is controlled. We are able to adjust the speed of the induction motor by controlling the voltage. How we are controlling the voltage is by using a technique called as sinusoidal pulse width. This is called sinusoidal waveform, or the technique what we are going to have, sinusoidal pulse width we are going to adjust. That's why it is called sinusoidal pulse width modulation technique. Ultimately, we are, by using this technique, we are able to adjust the speed of the induction motor. So that's why this is called a sinusoidal pulse width modulation technique. So we have a formula to find out the number of pulses produced, where P is called as the number of pulses produced in half cycle. Okay, so P is the number of pulses produced in half cycle. So what is the formula for P is this is Fc divided by 2Fr. So when you see this carrier frequency, so in this carrier frequency, how many carrier waves are there? How many triangular waves are there? 1, 2, 3, 4, 5, 6. So carrier frequency, I'm going to write down, this is 6 times that of the reference. For one reference, how many carrier? This reference is nothing but a sinusoidal. For one cycle, how many triangular waves are there? 6 triangular waves are there, divided by the original is 2 into Fr. Fr will cancel, 2 ones are 2 threes are. Therefore, how many number of pulses are there for an half cycle? 3 number of pulses should be there. So you can see here, how many pulses are there in the half cycle? 3 number of pulses are there. So that's why this is called pulse width modulation. And to vary the pulse width, you have one more formula where this is called modulation index. This is called modulation index. So modulation means control index or controlling index. Okay, so modulation index is defined as the magnitude of reference voltage divided by the magnitude of a control signal. So the magnitude of reference is sinusoidal divided by the magnitude of a triangular waveform. So this is how, by using this modulation index, by controlling the magnitude, we can control the waveform better. So automatically we can control the pulses. This is all done by using an G ratio. So this is all about the, I think our title is fulfilled. So power electronics, all these are power electronic switches, power electronic control of which motor? Induction motor. And what we are going done here, so ultimately by using this network, we are able to control the speed of the induction motor by using a technique called as sinusoidal pulse width modulation technique, where this plays a major role of controlling the speed of an induction motor by using an inverter. So this section I am going to call it as an inverter section. So this is how it is connected in star and how it is connected in delta. Hope I had given you the sufficient knowledge to understand the basics of this sinusoidal pulse width modulation technique. So if you feel the content is really useful, please like the video and please share with your friends. If you have any doubts, let me know in the comments section, and please subscribe to the channel, and please make your friends also to subscribe, which is like a free channel to help the public, those who are studying this electric vehicle subject or those who want to learn about this electric vehicle. So this is a free subject for the benefit of the students. Please try to encourage this sort of channel for having a good quality education. So thank you for your visit, and we'll meet in the next video of energy management systems of an electric vehicle. Thank you for watching. We'll meet in the next class.